pull down seal. There is a videos folder. Doesn't show up when you first log into D2L. So any videos I show in this class, and these are 2 that I have so far, will be in that folder. These were put together 3-4 years ago by Xilinx, and they've got a lot of good information. I'm going to periodically stop the video because I want to emphasize a particular point.
Hello, and welcome to this recorded e-learning on basic HDL coding techniques, part 1. My name is Frank Nelson. I'll be your instructor for this module. This module introduces the primary HDL coding techniques that most FPGA designers use for their design construction. This module introduces some of the primary concepts that impact the quality of results a designer will get when synthesizing for a Xilinx FPGA. This module also provides some detailed recommendations about creating effective HDL that will provide high speed and save FPGA resources. This module requires that the designer already know how to code with VHDL and or Verilog. Many of the topics discussed include HDL code in either VHDL or Verilog language. We do not expect the user to know both languages, but most designers can create code as described in this module. After completing this module, you'll be able to specify FPGA resources that may need to be
Down to the audio.
identify some basic good guidelines successful FPGA designers will use, select a good HDL coding style that provides fast and efficient circuits as well. But the key thing is that many new customers are disappointed that they're going to have to instantiate some of the most popular FPGA resources into their design. This is now pretty much standard operating procedure in the FPGA industry. What I mean by that is that most customers are prepared to create highly optimized cores with the Xilinx Core Generator or the Xilinx Architecture Wizard utilities, and are then going to have to instantiate them into their HDL. Now, this flow allows users to work around limitations all synthesis tools have with regards to automatically inferring the best FPGA resources. The bottom line is that all the high-end synthesis tools available for FPGA industry usually do not allow inference of all the best FPGA resources. That is usually the latest and greatest, like the DSP slice and block RAM resources. Now, synthesis tools may allow some inference of these resources. There are plenty of exceptions, but usually only primary applications are inferable. For example, the block RAM resources are inferable for memories that only use a single block RAM, are not initialized, and don't use the output register functionality. So simply put, it is too difficult for synthesis vendors to keep up with all the possible configurations of a single FPGA resource and build the ability for the users to infer all that possible functionality. So in the end, since most customers want the high-end resources, the newest resources, and all the functionality, that requires them to instantiate. To aid customers in building a desired component with complete functionality, we recommend that users build their components with a Core Generator or Architecture Wizard. When I mention high-end synthesis tools, I'm referring to the most popular synthesis tools available.
Core Generator. Core Generator is a design automation tool they have that gives you access to their library of components. So their second party IP. So it's got a search engine and all of that stuff, so you can say, I want this particular type of circuit. You can configure it any way you want to, and then it generates the module along with a file that will tell you how you would instantiate it into your design. So Core Generator is just their GUI that gives you access into their component library.
The FPGA industry, specifically simplified in Xilix's own XST. While this module is not about how to use those synthesis tools, it is important that users learn about proper use of their synthesis tool and their tool's limitations. Now, we provide some basic information about synthesis options in the Designing for Performance course, commonly called DFP. This module will discuss in detail proper HDL coding techniques for the most common and fundamental components designers make. get optimum speed, device utilization, and minimal power, customers need to plan on targeting as much of the FPGA's dedicated hardware resources as possible. This means that users not only have to plan on instantiating the proper resources, but sometimes have to look for creative ways in which to use the dedicated resources. For example, most customers would think to build a FIFO with the block RAM, but most would not consider building a finite state machine with block RAM. Very often, customers choose a device that has some dedicated resources left over. So to get the most out of the FPGA, users have to very often pack the most into the FPGA, and in particular, those dedicated.
Implementing an FPGA or a finite state machine in block RAM. The finite state machine will have combination logic, and it also has registers for state memory. The block RAM in the Xilinx FPGAs, of course, can implement the LUTs, but it also has registered outputs. RAM doesn't normally have a registered output, but block RAM in the FPGA that Xilinx sells, they are. That's what allows you to implement a finite state machine in block RAM in Xilinx FPGAs. And since it is hardware and not synthesized using CLBs out of the FPGA fabric, you wind up with a faster finite state machine if you implement it in block RAM.
Part of the resources they weren't using. Writing good HDL is of course important because it is used by synthesis tools to infer the most popular FPGA resources, that is, LUTs and registers. Since there's very often more than one way to code for effectively the same functionality, it is important to understand the differences between two different or more ways to code a function. This is compounded by the fact that often a poorly coded piece of logic creates a timing critical path for a designer to resolve later on, and often designers waste a great deal of time resynthesizing and repeating a place and route solution, hoping to meet a timing objective. Another very common FPGA design practice is for a designer to pipeline a timing critical path. Now this is done by inferring extra registers on a long data path so a long net delay or multiple LUTs in series can be tolerated.
We showed that on
If you are
the
not
last
familiar with
time.
pipelining, don't worry, we'll talk a bit more about this later on. Finally, to improve the speed of the output netlist made by your synthesis tool, it is important that you take proper advantage of the synthesis options available to you provided by your synthesis tool. And we'll talk more about this in the Design for Performance course, as I mentioned earlier, but we wanted to mention some of our general recommendations for driving your synthesis tool here.
Just as a comment there about different synthesis options. What that implies is that you are going to be synthesizing over and over and over and over again until you get what you want. Because every time you change a synthesis option, you have to resynthesize the design. And then you have to redo your timing analysis and everything. But you have to try these different options to get what you ultimately want. For example, you may tell the synthesizer, I want to do 100 encoded finite state machines. See what you get. You may then go back and say, well, let's try binary encoding and see if I can get higher performance. You have to resynthesize the design. So you should expect that you are going to synthesize over and over and over and over again before you finally get a design that meets all of your specifications. This is a tedious process.
This slide is trying to highlight some of the benefits of the dedicated hardware resources that exist in the newest FPGAs. The most useful of the dedicated hardware resources is the DSP slice and the block RAM resources. Besides using less power and saving primary FPGA resources, that is, LUTs and registers, using the dedicated resources makes it easier to estimate timing. This is because the architectural delays of the dedicated resources are known before place and route. Unlike data paths that may contain multiple LUTs and nets in series, data paths that use the dedicated resources do not require any programmable routing delays, except to route to and from the dedicated resource. Another reason to use the dedicated resources is that compared to soft implementations, now that means a LUT and a registered implementation of the same component. But compared to that, the speed of the dedicated hardware is significantly faster than, shall we say, a soft implementation. So be sure to use as much of the dedicated hardware resources as your design needs. And if you think you may be running out of primary FPGA resources, consider implementing more of your design with leftover dedicated hardware resources.
In other words, what he's saying is,
This slide describes the timing closure flow for Xilinx FPGAs.
whenever possible, use hard IP to implement your design. First of all, you're not using LUTs and registers in the FPGA fabric. That leaves them available for other uses. The timing is precisely known for the hard IP, so you're going to get a much more accurate timing analysis done. And finally, the hard IP is considerably faster than what you could implement using LUTs and registers. So there's several advantages in using the hard IP. You save resources in the FPGA fabric, you get a more accurate timing analysis, and you get a much faster design.
Wouldn't you save on power too?
Yeah, you might. I never looked to see how much power is consumed by an individual CLB to see how they compare. I've always looked at it from the standpoint of speed, but not power consumption. But there may be some advantage there as well. Incidentally, this diagram here shows you everything that's involved in creating a design. If you'll notice here, and rather than him going through this, I'll go through it very quickly and then we can speed on. You got your specifications, you have to determine good pin constraints. Where do you want, when you assign your pins, you don't want to have the inputs necessarily on one side of the chip and the outputs on the other. That's long data paths. So you code for the architecture. Different architectures provide different hard IP. Use the IP, the hard IP whenever you can. You're going to have to specify any global constraints, and that would typically be done through a user constraint file. So now you go into synthesis. Now you're going through your timing analysis. And if you don't meet the timing analysis, notice all these feedback loops, including this one here. Change the code. A lot of times you wind up changing the code. So once you do that, you then go over here and you use other design automation tools that do the placement and routing. Then you have to recheck the timing. If it meets your timing requirements, you're done. If not, re-architect the design. Go back to repartitioning, whatever you have to do, and go through the whole process again. FPGA design is not, I'm going to code up my design, simulate it, pass the simulation, run it through the simulator. I'm done. You haven't even started to do the work that you need to do. And as the hardware designer, guess who's responsible for going through this flowchart? You are.
You may recall this
Let me,
slide from the
skip forward
Essentials
a
of FPGA Design course. Most important efforts to improve design are used from the MAC functions, filters, ALUs, etc. So it's a very flexible component, and of course that can be challenging to infer all that functionality.
Here, I'm going to back this.
While I recommended coding decisions, and this explains why making good HTML code is critical and is most beneficial when good coding styles are used from the beginning of the design process. As I mentioned earlier, most designs will require at least some instantiation of dedicated hardware resources. This is because all synthesis tools have limitations on their ability to infer all of the FPGA resources. Now, this is especially common when the dedicated hardware has as much flexibility to be used in so many applications. So, for example, the DSP slice can be used for multipliers, large muxes, MAC functions, filters, ALUs, etc. So it's a very flexible component, and of course that can be challenging to infer all that functionality. While we recommend inference, if possible, when you instantiate components, try to place the instantiations in one location, usually at the top level of your design. This will make it easier to port your code to another device family or technology later on, while reusing as much of your generic HDL as possible. We also recommend using the core generator and, as I mentioned, the architecture wizard to create your optimized components. These utilities are a standard part of the ISE tools and, of course, are included with the toolkit. This is a short list of the most commonly inferred resources. For example, the shift register LET is commonly used to build delay elements or pipeline stages. It is easily inferred, but with the limitation that the outputs cannot be reset and its contents cannot be initialized. So if a user were to code for a shift register with a reset, there is no way any synthesis tool could infer the SRL. There would also be no warning or error message sent by the synthesis tool, since the tool would think you wanted to build a shift register with your standard flip-flops. There would be no error in that. Likewise, the implementation tools would not give a warning or error message, since the netlist made by the synthesis tool would reference flip-flops. And as we know, there's nothing wrong with that. You should also note that even if you were to build an appropriate shift register component, your synthesis tool may still require you to place an appropriate attribute in your HDL that will tell it to map to the SRL primitive. So one of the most helpful skills a designer can have is to have enough experience with their synthesis tool to know the appropriate attributes and its appropriate coding style limitations for that synthesis tool. One of the best ways to determine how to infer a resource is...
He says attribute, I say attribute. Also, he says in here SRAM, I say SRAM. Just
to go to support.xilinx.com and open the XST user guide. Now this is also associated with
we can go ahead. The thing you should get out of this,
it shows you how to infer the best FPGA.
This particular slide is that there are certain types of circuitry that the synthesis tool is always going to be able to infer. There are some that it might be, and then there's some devices that it can't.
Got the XST user guide. Now most designers are instantiating memory resources, I/O standards, including SerDes functionality, and clocking resources on every design. That is because there's just so much flexibility with this FPGA architectures that the synthesis tools just can't build a tool that will infer all the possible configurations that a customer might use. So you're probably better off planning to instantiate these resources from the beginning. As I mentioned earlier, we suggest that you keep your instantiated components in one location. Now, most designers place the Xilinx specific instantiations at the top, or one layer down or one level down, but never more than that. This makes it easy for the user to locate and maintain the design and port your code to another device family or technology later if necessary. We also recommend keeping your pin assignments and pin attributes in your design's UCF files, so all designing specific constraints are removed from the HDL. This makes your code more generic. Another instantiation option a designer has is to use the VHDL configuration statements or put wrappers around each instantiation. Now this will maintain the design hierarchy and still make it easy to swap instantiations if your design migrates to another architecture. Xilinx recommends that hierarchical optimization. Now that is a standard synthesis option that allows users to optimize common thread logic across a hierarchical boundary. Now we recommend that this hierarchical optimization be turned off. This is because synthesis tools will change node names and change the logic optimization on nodes that users will often want to simulate, probe, debug, or analyze the Allowing this optimization will sometimes make debugging nodes on a hierarchical boundary much more difficult. So in general, we tell our customers to leave this optimization across hierarchical boundaries off and only use it later as a final last-ditch effort to gain time enclosure. Fortunately, most customers...
Let me simplify this for you. Let's suppose I have this design hierarchy. It talks about maintaining the hierarchy and flattening the design. You can tell the synthesizer, optimize my code as much as you can to get the most efficient implementation. When you flatten the design, what you do is you say, I'm going to take this module and move it out of this level of hierarchy and combine it up here. It's a lot easier for the synthesizer to synthesize a flattened design than to try and optimize this and optimize this, because you've got different layers in the hierarchy that you're trying to optimize across. So when you flatten the design, you collapse the hierarchy. You take modules from this level and you move it to the next higher level. The opposite of that is maintaining the hierarchy.
Don't get this desperate, but we like to mention up here so that you have the ability to debug and simulate nodes later. Now, all synthesis tools will default to not allowing optimization across any boundaries. However, if you choose to enable this optimization, only enable it across the boundary associated with your timing critical path and never allow it to be used globally. Maintaining your design's hierarchical boundaries yields numerous benefits. As I mentioned a moment ago, it makes it easier to locate nodes when you are simulating probing with ChipScope, for example, or simply reading a synthesis or timing report. However, what many customers don't realize is that it also enables floor planning and use of the incremental design flow. Incremental design allows users to maintain the place and route solution found for part of the design and only repeat place and route on components that fail to meet timing or have changed logically. Note that most experienced designers know that for optimum speed, they need to make sure that critical timing hierarchical boundaries have registered outputs. This is a pretty standard way for users to tolerate a high fanout net that a component might be making, or if they know the placement of the destination logic might be far away. But commonly, when a designer makes a perfect complement to a piece of logic, adding a register can easily be accomplished by converting the component to a registered component. If the component already has its outputs registers, then optimizing across a hierarchical boundary will have no effect, since logic optimization won't remove a register in that case. You may recall that I mentioned it's important to be aware of what your synthesizer will generate depending on how you code a piece of logic. The first component we're going to look at are muxes. If you build a mux with if-then statements, synthesis tools will almost invariably build logic into priority encoders. Now, likewise, if you build it with a case statement, the synthesis tool does not give any signal a priority. So if you build a mux with if-then statements, note that the timing critical signal, that is the signal on the first if statement, ends up in the last logic stage. This signal will have to go through only one logic level and have the shortest delay. This is perfect for the case when you need one of the inputs to be faster than the other inputs. You may have also heard about that unintended latches or complex clock-enabled equations can be synthesized when your if-then or case statements do not cover all possible conditions. Now, fortunately, synthesis tools warn users when they are building latches, but they do not warn when long clock-enabled equations are being built. That is why it is important that you verify for yourself what is being synthesized by your HDL. To do this, the best tools provide schematic viewers that show when this is happening. So this example shows you that the if-then statement construction of a mux builds LUTs in series. Now, it is very important that you understand that having these LUTs in series produces long delay paths. Just look at the do_e input. Its path to the output requires 4 LETs and 3 net delays to be traveled before the output would be accurate. So this and the do_c paths are the longest and will be the most timing critical paths through this component. Conversely, critical_sig path will only have to travel through 1 LET. This is of course much faster. The component's construction was all inferred by the synthesis tool when we coded the MUX with if-then statements. Note that the order of the inputs to the if-then statements, the most timing critical is listed first, followed by each of the lesser critical signals, and ending with the least critical inputs in the statement. Now, if you build with nested if-then statements, be sure and watch your timing on your inputs because the LETs can cascade easily. Always be sure in this case to put the timing critical signals first in your HDL. However, the best solution is to build the component with a case statement as much as possible. Case statements do not build with LETs in series and tend to build the LETs in parallel, which is dramatically reducing the number of logic levels. If the last example was constructed with 4 LETs, it would require only 2 logic levels. Recall that the function had 9 inputs, which would require 2 LETs in series and a total of 3 LETs. So see if you can make that work and replicate what we expected and how the difference would come by using a case statement. Case statements are almost always the way to go when muxing logic. However, be sure to define all outputs in all branches. Otherwise, this will produce a latch and a warning message. To do this, we recommend using a default statement before the case statement. Case statements used in a register processor always statement can produce a long clock-enabled equation. So likewise, we recommend using a default statement before a registered case statement. Some other recommendations include registering the select inputs to your case statement. This is especially helpful if there are a large number of inputs to the multiplexer, since this component might require several logic levels to be constructed. Recall that the more logic levels in series, the more net delays in series, and this quickly adds up to a lot of delay. To work around this, registering the inputs to the select lines will effectively pipeline the large common serial path from the LETs used to generate the select inputs. Another creative solution to this same problem is to use one-hot encoded select inputs. One-hot encoding reduces the complexity of the logic generated by having only one signal represent the input.
So what he means by doing that is, let's suppose I have a 4-to-1 MUX. I would need 2 select lines, and depending on 0, 0, 0, 1, 1, 0, or 1, 1 on those select lines, determines which of the 4 inputs gets hooked to the output. If you use one-hot encode instead of 2 select lines, you have 4 select lines. And so all of the select lines are 0 except one of them. And that's the one that determines which output you have. So you have a select line corresponding to each input that you have. That's the one-hot encoding of the select lines.
So rather than having the 3 select lines that require decoding 8 possible combinations, we could use 8 select lines where only 1 bit is used to determine which input is selected. Lastly, test out building a MUX using a case statement with your synthesis tool. Usually synthesis tools will put the last signal listed in the case statement in the last level of logic, meaning that it will get the shortest path. This example shows a 6-to-1 multiplexer with binary coded inputs. Notice that a default value has been defined for the remaining possible combinations of select line.
Here the select lines are fully encoded. This is not the easiest thing to use here. Unfortunately, this doesn't show the window of what's going to appear. Now they have.
Be helpful if there are a large number of inputs to the multiplexer, since this component might require several logic levels to be constructed. Recall that the more logic levels in series, the more interseveral logic levels to be used to generate the select inputs. Another creative solution to this same problem is to use one-hot encoded select inputs. So rather than having the 3 select lines that require decoding 8 possible combinations, we can use 8 select lines where only 1 bit is used to determine which input is selected. Lastly, test out building a mux using a case statement with your synthesis tool. Usually synthesis tools will put the last signal listed in the case statement in the last level of logic, meaning that it will get the shortest path. This example shows a 6-to-1 multiplexer with binary coded inputs. Notice that a default value has been defined for the remaining possible combinations of select line values. This makes the implementation much smaller. XST used not only LUTs for this design's construction, but also took advantage of the dedicated muxes included with each slice. These muxes allow larger multiplexers to run faster and save LUTs. In this case, the result used fewer LUTs and got better performance by having the dedicated muxes available. This design also inferred a register on the data out signal. This effectively added a pipeline stage. Recall that this is one of the best ways to improve system performance in an FPGA. If this did not have a registered output, a critical path could evolve through the...
How do you know that has a registered output?
Registered output.
How do you get into the case statement?
On the clock.
You gotta have a clock edge. That's what registers the output.